Hello, everyone. My name is Chang Jie. I'm from Fortis, which is an institute in Munich. I'm going to present a joint work with my colleague, Ulrich Schöp. So this is the motivation of our work. So now here I have a program written by my colleague, and I want to check that if this program follows some secure programming guidelines. For example, I want to check if all the inputs have been sanitized. I want to check if all the accesses to sensitive data are authorized and are logged, and so on. And moreover, I want to check these guidelines continuously and incrementally. And why? Because I think if we have a lightweight tool for this, then we can help the programmers to avoid making some typical errors during their development. Okay, so we have this. We have a project called Guide Force, and in this project, we have developed several effect and type systems for lightweight static analysis. So here we are mainly using this kind of analysis for trace properties. Maybe the definition of traces are a little bit different. So firstly, let's assume that some functions of interest emit some event. So for example, a logging method of a server will emit a logging event. The close method for a database connection will emit a close event. And then think about execution of a program. This will generate a trace of events. It can be finite if the program terminates. It can be infinite if the program diverges. And a guideline is nothing but just a set of traces of events that are allowed. And the idea of our type system is to add effect annotations, and this annotation gives information about the possible traces that can be generated by the program. So for example, here we have the program, if a login succeeds, then it reads data, otherwise it closes the connection. And the type system will compute the type for this program, and I'll talk about the type later. Actually, this talk focuses on the types. And it will also generate like the annotation. Like here, we say, okay, there are two possible traces. One is locking and read. If the locking succeeds, the other one is locking close. And then type inference is nothing but just effect computation. We infer the type, and the type carries the possible traces that the program can generate. We can simply just check that like this effect is contained by the guideline. Remember that the guideline just tells us what are allowed. So we just check this. And if it is contained by the guideline, then yes, the program adheres to the guideline. So we are sure that the program satisfies those guidelines. Okay, so here I have already mentioned one key concept, the effect annotation. So for example, like in the verified authorization method, it will emit a else event. So it will generate a trace, say else here and so on. And as I say, in this talk, I'm mainly focusing on the types. So why are we interested in the types? So actually, we are working on a so-called region types. So what is a region? A region is just a structure that representing or just a name, okay? Some abstract things that represents the properties of values. And for example, you may think about a property, talk about the provenance information of the program. Like here, I have this created at L region. Like it tells us like in which line an object is created, for example, in your program. I have a null region to say, okay, the value is null. I have unknown, something to tell me that, okay, I don't know anything about this value. I have a tentic region to mean, for example, the string is tentic, like this string is entered by the user. So you should not execute a command that containing a tentic string, for example. And similarly with the untentic one and so on. And the point here is that having these region types, they can improve the precision of the trace property analysis, because then objects in different regions are analyzed separately. And a method with inputs in different regions, they will have different effects. You may think about like a run method that in some interface, and there are several instances implementing this interface. And if you say the run method should always have the same effect, then it's essentially useless, right? So you really want that like the different object in different regions, they should really have different effects. And of course, then we have to pay something. So in the previous work, we are in our typing inference algorithm, essentially for each method that are in different object whose object is in different regions, or the inputs are in different regions, we have to analyze their code in multiple times. For example, look at this example. There's this foo method, and we call the foo method of object 1 twice and object 2 once. And for the object 1, it is invoked with different inputs, input 1, input 2. And then for these 3 invocations, we have to analyze the code of foo 3 times in order to get the effects and the types of the method. And we want to, and this will make the analysis less efficient, and we want to improve this. And our idea to improve this is to have a type inference algorithm that analyzes only the code only once. And how, like, the idea of our new inference algorithm is that let's generate a summary for the method. These summaries capture like how the types changes in the program. And then later in the analysis, let's use this summary only, but not the source code. And we call our summary an abstract transformation or abstract environment transformation. And that, for example, like here we have a piece of simple code, and this is the abstract environment transformation look like. We'll go into detail now. So firstly, if you look at our transformation here, it consists of 2 kinds of things. One is essentially like the equality constraint. The second one is the subtyping constraint. And we have this equality constraint for each assignment, a variable assignment. So for example, like here, we have we assign x to y.f, the field f of the variable y. And here we will just say, okay, then the type of y of x must be the same as the type of the field f of some object of type which is the same as y. And this is quite similar to the constraint that we have saw in the previous talk. And similar, the second line here, we say, okay, we generate some new object and assign to y. So y must have the type C. Like, let's say here we assume that this object C has type C. And for the field, because we are working with weak updates. So when I say weak updates, suppose that you have a field in one object that has this type, in another object that has that type, and that essentially require them. This field should have the type greater than all these instances. So because of this, we cannot use the same equality constraint, but we have to use a subtyping constraint. We require that the type of f of y must be greater than or equal to the type of x. And then, okay, so this is quite similar to in the previous talk. You generate an equation for each node in your program, but here we generate constraints for the assignment nodes or some specific interesting nodes. And after that, we need to combine them, right? So we define some operations like composition and joins on these abstract transformations to combine these constraints in order to generate a transformation. And this corresponds to the constraint generation in some constraint-based analysis. And after that, okay, now we should start using it, right? This is just abstract notation, and we should instantiate it or concretize it to do the computation of the environment of the types. So now suppose we have some input environment saying that what are the type of y, what is the type of f, the field f in an object of type A, and so on. And then we can apply these abstraction function to the input environment, and then we get the updated environment. So this is what I call the instantiation of the transformation, and this corresponds to constraint solving in some constraint-based analysis. And lastly, okay, you have the updated environment, so you will be able to derive the return type of your program from the updated environment. For example, suppose now here my program returned y.f, then you can simply look at the environment here and then found that, okay, the type must be B. So in this way, you can compute the return type of your program. Okay, let's go into this in more detail now. So firstly, I would like to clarify something. So yeah, of course, I'm going to work with region types, but for the notion of abstract transformation, actually, we don't need to fix the notion of types. So here I'm going to work slightly more general. So I think I only assume a finite set of atomic types. So here I have a set of sims called A, B, C, D, and so on. Both they are finite. And then what I call a type, it is just simply a set of atomic types. And then because of this, I will write a button to denote the empty set of types. I simply write A to denote the singleton set A, and I write A or B or C to mean the set A, B, C, because the set of these types will represent the possible types, possible atomic types of my program. Okay, and then in the typing environment, I will also consider, as you see in the example, I will also consider the field typing. So for example, here it says that the variable x has type A, and the field f of any object of type A will have type B or C. So in my typing environment, I also consider field typing. And then let's think about the value in the constraint. Like when I say the value of constraint, I mean something like x must have value v, or the y.f must have value greater than v. What are these possible values? So here, the v here can be like a variable, because if, for example, you may assign x to y. So here, yeah, the value should be y. You may assign to a concrete object, which you already know the type. So the value here can be also a type. And you may assign it to a field. So, and it may not be just a field, but it may be a field pass. You may say, okay, assign x to the field y.f.g.h, right? So which means the value can be also access pass. And then it can be also a set containing all the above possibilities, right? Because you may have some some branches, and then you want to join all these possibilities together. Okay, but here you may see that I put a question mark here for the access pass. And why? Because it seems that working directly with these access pass may be problematic, because the length of this access pass may be unbounded. So here, a simple example. Suppose we have this node class for linked list, and this last method just compute the last node in a list. It's very simple. You just check that if the field next is null, there's no next node, then you return the current node. Otherwise, you call the last method of your next node. And then if you think about the return type of this method, it can be the same as the node as the variable this, right? Because if this is the last node, it can be this dot next. If next is the last node, it can be this dot next, and so on. So you get an infinite set of passes, and this will make your computation of your type non-terminate. So what shall we do? So yeah, the idea is quite similar to what we learned in the previous talk. Use abstract interpretation. And here I just select a specific one only, but we can replace this by the other finite abstract interpretation. So I choose the finite representation of access paths called access graphs. And then here's the idea. Like for example, like the variable here, this is the base of the graph, and on the right hand side of the arrow here, this will be like the graph of some fields representing the field paths. So for this one, I have the empty field graph. So this will represent only the paths these with no fields. And here I have only one node next and nothing else. So this will be like only one node and the empty set of age. And this will represent only the path, this dot next. And if I add an age from the node next to the node next itself, then this access graph will represent all the access paths of length, let's say greater than 2. So in this way, all the possible paths of this dot next and so on are represented by only these three graphs. So we have a finite representation of all the paths. And then, okay, now in our constraints, we will not work with paths, but we are going to work with the graphs. So we call, so firstly, for the graph, we work with a slightly generalization. We allowed the base here to be either a variable or a type. You may remember these field typing, like where we write a.f, so the base can be also a type. And we call here we call a set, which we write as a disjunction form. We call a set of such paths, a set of such graphs, a term. Okay, so this will be the value of the constraints. So we have this equality constraint for variable and some subtyping constraint for the fields. So these are our constraints. And then what is an abstract transformation? It is just a set of constraints, or it is a map from some keys to the terms. So because this is a map, so it requires that all the terms, all the keys here, like xi's and the graphs bg, they should be different. Moreover, we require that the terms for variables should not be the same as the variable. So because if you say I'm assigning x to x itself, the variable x to x itself, essentially this means nothing, right? The type of x does not change. So we simply just omit it by just say, okay, we do not allow this to appear in the abstract transformation. And similarly, for the subtyping relation, the bottom, the empty type, of course, this will be the least one in our types. And then if you say, okay, my type should be greater than the empty type, then of course essentially this says nothing. So again, we just omit it in our definition of abstract transformation. Okay, so this is the example we have for before. So if we look at the constraints here, that the first one says that x should have the type y.f, and y should have the type c, and then c.f should have a type greater than y.f. So here you can see that there are some substitution performed here before that in the code here is y.f, but in the transformation here it becomes c.f. So we are going to define some operation to perform such things. So firstly, we should do a sort of instantiation of this operation. This is just some symbolic representation, and then but it can be concretized or instantialized to a function on environment on typing environments. And this instantiation procedure is essentially just a fixed point algorithm to solve the constraints that we learned in the previous talk. And because our representation of the graphs and the terms and so on, these things they are all finite, and we can see that later our operations are always they are monotone. So actually we have a guarantee that this algorithm always terminate. And the difficulty here is that because we are working with the subtyping constraint, and the term there, the values there, they are not concrete paths. They are actually some graphs that represent a set of possible paths. So this will be, the algorithm here is quite different from the literature. So we have to, the difficulty here is that we have to find some reachable fields in the paths, in the graph. So in your graph, you have many paths, and then you need to find out which one are reachable from your typing environment, and then you need to join the value together. Okay. And then for composition, of course, we want to compose two transformations. And then, so the composition here is quite similar to variable substitution. So for example, by the way, when the right one would be the first transformation to instantiate. So you will firstly instantiate this x to c. So x will have value c, type c. And then when you do composition, you need to substitute the later one or the appearance of x by the type c. So that's composition. And then similarly, we also need the join operation to model branches in the program. So here I defined the join operation just pointwisely. So for example, here you assign x to c, and in the second one you assign x to d. And then in the joint one, you have to join C and D together and assign it to X. And for Y, you have to join Y or Z, because you may remember that like the identity assignment is essentially omitted in the definition. So you have to join it back. Okay, then we have the theorem, okay, to say something like, okay, this operation, this composition and join, they are correct. And then you may expect that, okay, if you update the environment with theta one transformation first, and then update it again with the other one, it should be the same as doing the composition first and then updating it secondly. But actually, we have only that this update is smaller than the update of the composition, and that's because we are now working with the abstract interpretation of the past, right? And this abstract interpretation will always introduce some imprecision, yeah, right? And but this is actually okay. I mean, this does not affect anything about the soundness of our typing algorithm, because if you look at the left-hand side here, this is essentially what happens in the previous typing algorithm. It will say, okay, I want to compute the type, so I need to start from the beginning of the graph, and then I do update the type again and again sequentially, right? But the right-hand side is saying that, no, I don't want to do that one by one. I want to combine something first, and then later I use this combined operation, combined abstraction transformation to update the environment in one. And of course, our combined one is less precise than the original one. And that's something we have to pay, right? We have to trade off efficiency by precision or the other way around. There's nothing for free. Okay, so these are the operations. And then now we can start talking about the type inference algorithm now. And we work with some types, region type system. Now we're going to work with region types, but and we work on some region type system on Federated Java. And here I will not go into the detail of the type system and so on, but here just to say that now we are working with regions, okay? So our type inference algorithm has two steps. In the first step, we are going to compute an abstract method table, or we are going to compute a summary of our methods. So we have this table T, and so for each class and for each method in this class, we will compute two things. One is the abstract transformation sigma. So this sigma, it captures the change of types in the method M. The second one is a term U. You may remember the term is just a set of graphs representing the possible return type of the program. So we have this term U, which will be instantiated to a return type of M. And how do we compute it? Essentially, this is computed via a fixed point algorithm and using some operation to compute the transformation and the term for each expression of Federated Java program. So for example, like if we have some if then else statement, then essentially we compute the transformation of one branch and the others, and then you join them. If you have the lacking statement, then you will compute the transformation for the two statements and then compose them. And then here you can see that for variable assignment, we will use equality constraint, and for field assignment, we will use the subtyping constraint. And for method code, we simply use the T that we compute in the previous round of the fixed point algorithm. And in this way, we compute a table, and this table summarize how types changed in the program. And then in the next step, we simply use this table T to compute the method and field typing of the program. So here I just do a simple example. So suppose now we want to compute the type of the method M of class C. So, and we suppose that, okay, now this method M lives in some region R, or some object in region R, and the inputs of M are in some region S1 to Sn. And then, yeah, and then our first thing is to apply our table T to find the abstract transformation for the method M. And then after that, okay, now we can form a context like these regions here give us the initial context together with from the field typing. We also get the types of the fields. And then we simply use the sigma to update this environment. In this way, we get the update environment inf. And then from this updated environment, we can use it to instantiate the term that representing the possible return type of the method. And in this way, we get the final return type of the method. Yeah, okay, I think I can conclude now. So in this work, we introduce a theory of abstract transformations, and we use them to summarize how types are changed in a program. And then in the analysis, we will use this abstract transformation rather than using the code. And in this way, if you need to analyze, if you need to compute the type or analyze the type of method from different inputs, different objects, then you don't need to reanalyze the code. You simply use this abstract transformation. And this can help to avoid redundant code analysis. And even though in this talk, I omit the effect part in the algorithm, but this algorithm can be extended to capture also the effect, the trace effects. And this will give us a more efficient region and region-sensitive analysis of trace properties. We only briefly discussed this in the paper, but we are currently working on the implementation of the algorithm to support also trace analysis. Okay, and that's all. So thank you very much for your attention.
Thanks, Chongqi. Any questions? Yeah, we have two.
Thanks. What are you using the analysis for? So you're doing this analysis and it's more accurate, but what does it enable you to do?
Yeah, so this is our, well, we want to use this analysis to check that if certain programming guidelines are satisfied.
Okay, so find bugs, basically.
Yeah, to find bugs, exactly, yeah.
Do they enable any kind of optimization or runtime behavior or something? You can benefit from just not just the bug-free kind of guarantee.
To improve
some performance,
some performance.
Yeah,
that's interesting. I mean, we didn't think about that. But I think because in our implementation, actually we allow if a program doesn't satisfy the guideline, then we can generate a counterexample in the sense of execution path. I think this can help the efficiency in the implementation, not the development, not the efficiency of the program. Yes. Thanks.
Does your analysis extend to support generics?
To support generic? No.
No. Have you thought about whether that would be feasible, or do you think it's just too hard?
What kind of generic do you mean? Sorry, maybe you can make it more concrete.
Generics.
Polymorphism.
Polymorphism. Oh, if you say polymorphism in the sense of class polymorphism,
in the sense of programming language polymorphism. So,
oh, okay. Parametricity. Yeah, I think it is doable. Yes, but I don't know. I don't have a Thanks.
Yes, so when I was at the talk, I was immediately reminded of Rust and the type system that exists there to ensure you have memory safety. So basically, this is your programming guideline, right?
Yes.
So do you have plans to support memory-related guidelines and in that sense concurrent setting?
Yes, I think it is definitely doable, but I do not have such a concrete guideline in mind. And moreover, we are targeted at Java. So at least for Java, this doesn't seem to be helpful.
So you just rely on JavaScript?
Yes.
Have you tried using this on higher order code? So,
yeah, that's a good question. Yes, in one of the papers in this project, they really consider about higher order programs, but there we're focusing on the effect part, using some abstract interpretation based on Bookie automata. But there we do not really think about region types, so it's not that related to this work. Sorry. Well, yes, we did think about that. Yeah.
Any questions? Okay, well, I guess that's time. Thank you very much, Chongqi.